Hi, I'm Mrs. Edwards, and today we're going to go over parent functions. Once we have down their equations, the shape of the graph, and the names of them, we're going to move on to transformations, reflections, stretches, and compressions. So let's take a look at the first one. The equation is y equals x. The graph of y equals x is just a line, and the name of it is linear. Y equals x squared looks like a U shape, sometimes called a parabola, but the equation is a quadratic. The third one, y equals x cubed, that one looks like something that is kind of sloping up there, and it goes through 0, 0. It's called a cubic. The fourth one, y equals the square root of x. I think the square root of x is easy to remember the shape because the symbol square root looks like something and it curves on over, and the graph starts at 0, 0 and then it curves on over. It looks a bit like the symbol square root of x, and those are called square roots. Next we have y equals 1 over x, and the y equals 1 over x has a horizontal asymptote and a vertical asymptote that are your x and y axes, and then they're kind of like two little half moons that curve on in there. That's known as the reciprocal function, because if you had x, if I flipped x over, we would have 1 over x, so reciprocal. Y equals e to the x. E is like 2.71-ish, and but really we're talking about y equals 2 to the x, 3 to the x, 4 to the x, e to the x. These are all exponential functions, and they skyrocket very quickly. They get really close to the x-axis, and then they shoot up very, very quickly. Sometimes you'll hear these ones referred to as the J curve. I'm not a big fan of that description because a J makes you think that you're going to come up, you're going to come up on one side, but then a J comes up here. And the functions, they do not come back up on the other side. It draws closer and closer to the x-axis the further we move to the left. This particular one is e to the x, but again, 2 to the x, 3 to the x, 4 to the x, e to the x, they are all exponential functions. As far as the vocabulary goes there, notice that the variable is in the exponent, and it's called an exponential function. All right, our next one, y equals sine of x. Most of you are familiar with sine and cosine of x. They oscillate between 1 and -1. Usually you just forget where to start. So for a sine curve goes through 0, 0 and then starts heading up. And I remember the sine curve because if you were going to sign your name on a check, you would start on the line itself for your signature, and then you would continue on. So we're starting at 0, 0 and then starting to sign. And those are called sine curves, of course. Next, we have y equals cosine of x, and cosine of x looks like that, almost exactly like the sine of x, oscillating between 1 and -1. Right. Next, we have y equals the absolute value of x. I think that the absolute value of x is another one that is kind of easy to remember the shape, because those absolute value lines there, those straight lines, if you grab those straight lines and then just brought them together, it would come together in a very sharp spot there. In math, we call those cusps, but it looks like a V. So the absolute value of x looks like a V, and it looks very similar to the quadratic, other than the fact that it comes together in a sharp spot, known as the absolute value parent function. Next, we have y equals the natural log of x. But again, logarithms, if you have ln of x or you have log of x, which would be a base 10, or log base 2 of x, all of those are parent functions. They all have the same basic shape. All logarithms, the basic ones, the y-axis is an asymptote, and then they curve on over. But when they curve over to the right, they curve over so slowly. Think about them like the lazy logs. It takes forever just to get up to a height of 2. It's going to keep climbing forever, but just so very slowly. This one happens to be a natural logarithm, but if I just said logarithms, it'd be the log of x. All right. This crazy one here, this is called a logistic curve, and the x-axis is a horizontal asymptote, and then we also have this asymptote above it, and then it curves in. It almost looks like a cubic on its side. We will not be spending a lot of time on the logistic curve. That is not one that you have to know for a test. You start to study it a lot more in calculus. And then y equals int x stands for the greatest integer. And the graph of a greatest integer looks like this. You can see why it is also called the step function, because it kind of looks like some stair steps. You will not be responsible for this one either, but what the greatest integer function does for you is when you substitute in an x, if you picture the number on the number line and then you just move to the right to the integer, like the answer is the integer on the right. So if I was at 0.1, I would have the answer of 1. If I had 0.5, I would have the answer of 1. If I had 0.9, I would have the answer of 1. And if I have 1, well then 1. But if I get to 1.1 and I substitute that into the greatest integer, I'd be at 2 because it's the next integer. You have to be a little careful because sometimes people think of it as rounding up, which is essentially true, but with negative numbers, sometimes you can get a little bit confused there. If you were at negative 0.9, for example, yes, you are very close to negative 1, but you're going to the next biggest integer. So negative 0.9 substituted in would give you 0, or negative 0.1 would have an answer of 0. So greatest integers and logistic curves you won't have to know too much about, but they are technically a part of the 12 basic parent functions. Now let's move some of these parent functions around. But how they move, these transformations, depend a lot about the location of where you're adding or subtracting a number, whether you are inside or outside of grouping symbols. So let's look at some examples. If I had y equals x squared, my grouping symbols, we don't see them, but they're around the x. And let's say that I had g of x equals x minus 1 quantity squared. So that minus 1 is inside of grouping symbols. The minus is going to move the parent function right. Yes, you did hear that right. A minus is going to move it right. So if I drew in the parent function y equals x squared, and I grab that whole thing and just drag it to the right one, we now have the graph of g of x equals x minus 1 quantity squared. The same thing would happen with a cubic. Let's look at a square root of x. Inside of grouping symbols, the square root symbol is a grouping symbol. And so if we have a minus 1 underneath the root symbol, then the minus is going to take us right. So here's a picture of the parent function y equals the square root of x, and we're just going to grab that and drag it to the right. Drag that to the right, and I now have the graph of g of x equals the square root of x minus 1. Next, we have f of x equals 1 over x. I just want to point out especially that the grouping symbols, it's the denominator. If we had an x minus 1 located in the denominator, then that minus 1 would be considered inside of grouping symbols, and we would take those two half moons and we would drag everything right 1. Y equals e to the x, the grouping symbols, that is where the exponent is located. So if I had e to the power of x plus 1, if x plus 1 was in the exponent spot, we would take that j-looking curve and we would drag it to the right 1. So grouping symbols for exponentials is up in the exponent. Grouping symbols for reciprocal functions is the denominator. Grouping symbols for a root is underneath the root. Y equals the sine of x. Whatever you're taking the sign of, that's your grouping symbols. If I had y equals cosine of x, again, whatever you're taking the cosine of, that's grouping symbols. Let's do a quick example there. If I put in x plus pi, that plus pi is inside of grouping symbols. So we would want to take the cosine curve, and because of the plus inside of grouping symbols, we would drag it left pi. And dragging it left pi actually makes it the sine curve. Okay, let's look at another example. Let's say I have g of x is x cubed plus 1. What I want you to notice now is that plus 1 is not inside of grouping symbols. If I had x plus 1 raised to the third power, then the plus 1 would be inside grouping symbols. But since the plus 1 is not inside of grouping symbols, when the adding and subtracting is outside of grouping symbols, plus takes you up and minus takes you down. So I would want the parent function of x cubed, and then I just grab that cubic function and move all of it up 1, and the graph of g of x equals x cubed plus 1 looks like that blue curve. Here's another example. We have g of x equals 1 over x minus 2. This comes from the reciprocal function, and the minus 2 is off to the side. In other words, the minus 2 is outside of grouping symbols. If this would have been 1 over and x minus 2 would have been sitting in the denominator, then we would consider the minus 2 inside of grouping symbols. But because the minus 2 is outside of grouping symbols, minus is going to take this reciprocal function and drag everything down 2. Keep in mind though, everything means the asymptotes as well. And the y-axis is an asymptote, but it goes forever up and forever down. So if you drag a line that's vertical and you drag it down, it's not actually going anywhere since it goes up forever and down forever. But the horizontal asymptote and those curves, those half moons, those are going to come down. All right, so the final graph would be those two blue curves. That would be the graph of g of x equals 1 over x minus 2. We just looked at how adding and subtracting inside of grouping symbols moves a parent function around. But now let's take a look at what happens if you multiply a parent function by -1 versus replacing an x with a negative x. These two are often confused for one another, so I'm going to multiply by -1 and then right afterwards replace x with negative x so that you can have a comparison of how those functions start looking a little bit different. Let's start with f of x equals x squared. If you multiply that by -1, then we're going to have negative x squared. Here's a graph of just y equals x squared, our parent function. Multiplying x squared by -1 is going to reflect it across the x-axis. So the graph of y equals -x squared would look like that. Next, let's replace the x with -x. If you're using really good notation when you make a substitution, whatever you're about to substitute should turn into a set of parentheses, and then what you want to replace it with goes inside of those parentheses. So instead of x squared, I have -x to the second power. Well, -x multiplied by -x is positive x squared. But we just said replacing an x with a -x should reflect the graph across the y-axis. Here is a picture of y equals x squared. But think about what it would look like if you reflected it across the y-axis. It's not going to change at all. So replacing the x with -x actually has no effect. But technically what happened was a reflection across the y-axis. Looking at f of x equals the square root of x. If I multiply that function by -1 and simplify, -1 times the square root of x is negative root x. That negative does not go inside of the root when you multiply by -1. So then if the gray one is a picture of the square root of x, if you reflect that across the x-axis, the red one would be a graph of negative root x. Similarly, if we replace the x with -x rather than multiply root x by -1, we would have the square root of -x. That negative is not going to come out of the root, so that is a replacement. When you see a negative inside of the grouping symbol, that was an x replaced with a -x. And what ends up happening is the square root of x would have been the gray one. If you reflect that across the y-axis, we have the purple one. So y equals the square root of -x is that purple graph. The function is 1 over x if we have a reciprocal function. If I multiply the reciprocal function by -1, well, -1 multiplied by 1 over x is -1 over x. A negative on a fraction could go with the numerator, the denominator, or out to the side. If I replaced x with -x, I have 1 over -x. Well, that's equivalent to -1 over x. If you were to reflect the 2 half moons, that reciprocal looking function, across the x-axis, or you were to take it and reflect it across the y-axis, the look of it would be exactly the same. So if you were to see a picture of a reciprocal function and it had been reflected, you wouldn't know if the original equation, the x was replaced with -x, or the function 1 over x was multiplied by -1, because they have the same result. Okay, we have an exponential function. X is sitting in the exponent spot, 2.7 to the x. If I multiply this by -1 and simplify, I get negative e to the x. So if we took that j curve, we would then reflect it across the x-axis to get the look of y equals negative e to the x. But if I replace the x with -x, we get y equals e to the -x. I want you to start noticing a pattern of how that looks different. In the x squared, it's not much of a difference because you don't really see the grouping symbols as dramatically in these small ones. But here, outside of the grouping symbol, the square root is my grouping symbol, outside is a negative versus inside the grouping symbol is a negative. So if the negative is outside the grouping symbol, the function was multiplied by -1, but if the negative is inside of the grouping symbol, then the x was replaced with -x. Here, there is a negative in front of e to the x versus a negative up in the exponent. The exponent is considered the grouping symbols, so here, notice the negative is inside grouping symbols where here it is not. So when the negative is not inside of grouping symbols, then we reflect across the x-axis. When it is inside of grouping symbols, then it's going to be a reflection across the y-axis. Okay, here's another one. So we have y equals absolute value of x, that's our v curve. If we multiply that by -1, we'd have negative absolute value of x. A negative cannot be distributed through an absolute value. So notice the negative is on the outside of grouping symbols. And so we would take that v curve and we would reflect it across the x-axis. If I replace the x with -x, I would have the absolute value of -x. And so if you took that v curve and you reflected it across the y-axis, it's not going to do anything. It's kind of like that x squared one. We're right back to where we start because absolute value of x and absolute value of -x are equivalent. If I have a logarithm, if I multiply it by -1, we have -ln x. So if you were to take that really lazy function, the one that's close to the y-axis and then slowly curves over, you would take that one and reflect it across the x-axis. But notice if I replace the x with -x, that negative is inside of grouping symbols. And so we would, to get the graph of y equals ln of -x, we would reflect across the y-axis. Now we're going to look at the effect of multiplying a function by a number that is a tiny number. If you multiply by a number between 0 and 1, well then your answers get smaller. That was kind of a big aha when you got to fractions and you're like, what? I thought multiplication always made things bigger. But then you took half of 10 and got 5. So if we multiply by numbers that are between 0 and 1, it's actually going to vertically compress. And then if you multiply by a number that is greater than 1, it is going to vertically stretch. If you can kind of picture a coat hanger, like something made out of wire, and it's in the shape of a U. If I had that coat hanger in the shape of a U and I grabbed both ends and I stepped my foot down in the middle and then I pulled up, stretched, it's going to, that curve is going to get narrower and it's going to get higher really quick. Okay, but if you took that same wire curve and you grabbed both sides of it, and when you grabbed both sides of it, you stepped on the middle again, and instead of stretching, you pressed down, you compressed, then it's going to bow out wider. Okay, so multiplying by a number that is tiny, between 0 and 1, it's going to be a compression. Sometimes you hear that called shrink, and that's fine if you'd like to refer to it as a shrink. Let's look at a couple of examples. Here is f of x equals absolute value of x. And then we have another function. The only difference between f of x and g of x is g of x is 2 times absolute value of x. If I want to graph g of x, I would start by graphing the parent function, absolute value of x, and then because we're multiplying by 2, it's going to be a vertical stretch by a factor of 2. Ultimately, what that means is all the y coordinates, all the heights, are twice as tall. If we look at a couple points just to emphasize that, on the parent function, y equals absolute value of x, that would be the coordinate 1, 1. So at x equals 1, the height is 1. If we double the y coordinate, notice that point is twice as high. But if we were here at 0, 0, that one didn't go anywhere because if the height is 0 and I double it, it's still 0. But each point on that parent function just went up twice as high. Here's another one. Let's compare what happens if I had a half absolute value of x. Well, the parent function being absolute value of x, there's that V curve. But instead of stretching it, it's going to compress it. So it's going to widen that out, and it'll be half as tall. In other words, if that was the coordinate, let's say 2, 2, well then on the blue one, on 1/2 absolute value of x, instead of being at a height of 2, we would be half as high, so half of 2, which would be 1. So notice that point is half as far off of the x-axis. We had a vertical compression. Now the other thing that's a little funny is when you say compression, you're not going to say 1/2 because it's twice as short. So we're going to say vertical compression by a factor of 2. If the fraction out there was 1/4, we would say vertical compression by a factor of 4. Let's look at just one more. Let's say I had f of x equals 2 to the x, an exponential function. Compare that to what happens if I had 3 times 2 to the x. I selected this one on purpose because it's really common for students to accidentally then say, oh, and that simplifies to 6 to the power of x. You cannot multiply 3 and 2. That would be doing multiplication before exponents. That 3 stays off to the side, and 3 times 2 to the x is not equivalent to 6 to the power of x. All right, so if we had that J curve that was 2 to the x with that horizontal asymptote, it skyrockets there. Well, this one, it's going to be a vertical stretch by a factor of 3. All of the coordinates on this original function 2 to the x, they're all just going to be 3 times higher. So if I substitute 0 into this function, that equals 1. 2 to the 0 power is 1. So if this is at a height of 1, 1 times 3, that's going to be up here at 3. Here's another point on the original 2 to the x. Let's say that this is over here at -4. Then if this was 2 to the -4, this would be 1/16. But times 3, it would be 3 times higher. So instead of being 1/16, it would be up at 3/16. And then here we want to have the next point that's on our g of x 3 times higher. So there's a sketch of the curve. Now notice the horizontal asymptote did not move because it's at a height of 0, and 0 times 3 is still 0. Here we go. Rapid fire examples. Graph x squared plus 3. Well, it comes from the parent function y equals x squared. When you add 3 outside of grouping symbols, we're going to move that up 3. So if we slide that up 3, here we have the graph of y equals x squared plus 3. Y equals x squared minus 2 comes from the parent function y equals x squared. Minus 2 outside of parentheses, we're going to move it down 2. So if I grab that y equals x squared and drag it down 2, there we have the graph of y equals x squared minus 2. Quantity x plus 3 squared. The parent function is still y equals x squared. Since we're inside grouping symbols, the plus 3 is going to move us left 3. So grabbing the parent function and dragging it left 3, we now have the graph of y equals x plus 3 quantity squared. X minus 3 quantity squared. Parent function is still y equals x squared. Minus 3 inside of grouping symbols is right 3. So if I take that parent function and drag it right 3, we have the graph of y equals x minus 3 quantity squared. 3x squared comes from y equals x squared. Multiplying by a number larger than 1 is a stretch, so we have a vertical stretch by a factor of 3. And then we grab the whole parabola here and just stretch it up times 3. In other words, what happens is all of the points are 3 times higher, so it ends up looking narrower. Y equals 1/2 x squared comes from y equals x squared. Because it's a number between 0 and 1, it's going to be a vertical compression. Notice, by a factor of 2, not by a factor of 1/2. So when you say compress, that means you're already squishing it, and it's twice as squished. Okay, so if I grab that parabola, y equals x squared, and I compress it by a factor of 2, it really means all of those points, they are going to be half as high off of the x-axis, so it gets narrower, or excuse me, it gets wider, and we have the graph of y equals 1/2 x squared. If I multiply the function by -1, it still comes from y equals x squared as the parent function, but multiply by -1 is a reflection across the x-axis. So I take that parabola and reflect it across the x-axis, and I have the graph of y equals -x squared. We're going to put several movements together, stretches, compressions, movements, transformations, together in the same equation. And when you do that, the order that you move something around or stretch it matters. So for example, just visualize for a second a parabola. If you were to take the parabola and reflect it across the x-axis and then shift it up 3, versus taking the parabola and shifting it up 3 and then reflecting it across the x-axis, the look of your final graph would be substantially different. So this is why the order that you perform these matters. So silly story in hopes of helping you to remember the order. You wake up in the morning and you stretch, and then before you walk out the door, you check your reflection, make sure you don't have any toothpaste on you, and then you're ready to move about your day. So as you are listing out how you want to move these parent functions around to get the final graph, I want you to keep in mind that you want to list out your stretches and compressions first. Then you want to list out the reflections, x-axis or y-axis. It doesn't matter the order. If there was a reflection across both of them, it doesn't matter if you say the y and then afterwards the x, just do your reflections next. And then lastly, your movements. And again, it doesn't matter the order there. If you say up and left or you say left and up, those will be the same thing. Let's take a look at some equations where we have more than one transformation, reflection, stretch going on. We're going to describe the transformations, and then after that you should be able to sketch what the final graph looks like by making little light sketches along the way, because this would be without a graphing calculator. But let's just focus on how we want to word it. For time's sake, I'm making every parent function y equals the absolute value of x. So you're picturing that v function, and then here's what we're going to do to that v function so that we can graph these equations. Here, we're going to stretch by a factor of 2. We wake up in the morning and we stretch. Stretch is listed first. The -3 inside grouping symbols is going to take us right 3, and then the +8 is going to be up 8. Here's another equation. Wake up in the morning and stretch. We don't have any stretches or compressions. So next we're focused on check our reflection before we walk out the door. This negative out front That is because the function was multiplied by -1, multiply. So we're going to have a reflect across the x-axis. And then inside grouping symbols, that +3 is going to move us left 3. And then -4 outside of grouping symbols is down 4. Here's another one. We do not have any stretches or compressions, no multiplying by a number greater than 1 or between 0 and 1, but we do have a reflection, the -1 in front of the absolute value here. That is going to make us reflect across the x-axis, and then the +3 inside of grouping symbols is left 3. The -9 outside of grouping symbols is down 9. All right, now this next one, just when you feel like you have it down, I'm so very sorry, but there is an exception. So let's start with it, and then we're going to tweak it just a little bit here. 0.5, that is a compression because 0.5 is the fraction 1/2. So I wake up in the morning and I stretch, so stretches and compressions first. So compression by a factor of 2. Then I'm going to do any reflections. Now this negative on the x is inside grouping symbols. So that was not multiply by -1, that was replace x with a -x. So we're going to reflect across the y-axis. Danger, danger. Anytime you have a -x inside of grouping symbols, what's going to happen is the right and left is going to be the opposite. Notice that inside grouping symbols, -3 was right, +3 left, +3 left. Normally, +3 would be left. But anytime you have a -x inside of grouping symbols, then the right left is opposite. So the +3 is going to be not left 3. Whew! Let's summarize. You wake up in the morning and you stretch. You list stretches and compressions first. If you have multiplied by a number greater than 1, that was a stretch. And if you multiplied by a number between 0 and 1, that's a vertical compression. But keep in mind, if you were multiplying by 1/6, you would say a vertical compression by a factor of 6. Okay, then we have check your reflection before you walk out the door. So reflections come next, whether it's across the x-axis or the y-axis. But if you multiply by a -1, and usually what that looks like is a negative outside of grouping symbols, then you have reflected across the x-axis. But if x is replaced with a -x, which usually looks like a negative inside of grouping symbols, well then you have reflected across the y-axis. Danger, danger. If you have a -x inside of grouping symbols, that is going to affect something else. So we're going to table that. And then lastly, you want to list your movements. So you stretch, you check your reflection, and then you move about your day, right, left, up, down. If your addition or subtraction of a number is outside of grouping symbols, then plus is up and minus is down. If you are inside grouping symbols, then addition is left and subtraction by a number is right, unless, danger, danger, we're bringing that down there. If there was a -x underneath a grouping symbol, then if we have add a number inside of grouping symbols, it's now going to be right, and subtract a number inside of grouping symbols will be left. Okay, so just remember that -x inside grouping symbols throws the rules off just a bit. All right, well, got a lot of rules here. Let's move it, let's go. See you next time.